Hi everyone, welcome back to chapter 2. So this is going to be part 2 of research methods. So we left off on Monday's recordings, or the last recording, on going over correlations. So I'm just going to review a little bit and then we'll move on. So remember, correlations looks at the relationship between two variables. So you measure, not manipulate. And so we're just going to go over a little bit more on the strength of correlations. So remember, correlations, we talk about a correlation coefficient, which is represented by the letter R, and that will tell you how strong a correlation is, whether it's strongly negative or strongly positive. So a -1 is strongly negative correlation, and a +1 would be a strong positive correlation. So we have a perfect correlation, can either be a +1 or -1. And then positive correlation is anything happening in between kind of 0 and +1. And a negative correlation is anything between a 0 and a -1. Now remember, a positive and negative correlations does not actually include 0. If you have an R of 0, that means that there is no correlation. So how would you graph that? So here's an example of some graphs. And when we're graphing it, how we get the R is kind of what we call a line of best fit. So you're trying to draw a line through the dots that best connects all the dots, or represents all the dots. So with an R of 0 on the top left hand, there's really no line you can draw that would represent all the data in just one solid line. Whereas on the bottom middle, then we have an R of 0.9, so that's a pretty strong correlation. You could easily draw a line for a positive correlation going up, kind of how if you see my cursor. And then we have all these other correlations in between, where again it's a positive correlation, but it's not nearly as strong as an R of 0.9. So that's what strengths of correlations look like. And of course, for negative correlations, it'd be the same thing, but going from the top left to bottom right instead of bottom left to top right. So again, here's just kind of some diagrams of what correlations could look like. So again, if all the dots line up perfectly into a straight line, then we call that an R of 1. Whether it's perfectly like straight up and down diagonal, or if it's slightly to the side, it doesn't matter as long as it makes a perfect line. The only exception would be a perfect horizontal line. And then clusters of dots, that's what you'll usually see when you graph a correlation. And then on the bottom, these are just some really fun drawings of what an R of 0 could actually look like, because if you were to average all of this out, you would get a perfect horizontal line. So why do we use correlations? Because you can't tell causation, so why should we even bother? So correlations are great because they make knowledgeable predictions about the future and past. So if we know something has a high correlation with something else, we can actually use that to predict how, say, behavior will change in the future. And then we can also, it's bidirectional. So A is correlated with B, which also means that B is correlated with A. So you want to think of that as bidirectional. So just the example before was when you guys laugh at my jokes, I get happier. But also, the happier I am, probably you guys are going to laugh at my jokes more because I'm more likely to tell a good joke on a happy day than a sad day, right? So those are some correlations, but not causation. So if I'm happier, I'll tell better jokes. When I tell better jokes, it makes me happier. So bidirectional. So correlations can also give an idea of which variable to use in an experiment for later on when you do want to determine causality. So while correlations don't determine causality, you can actually use them to help predict future experiments where you will be looking at causality. And then, of course, they're great for when you can't manipulate variables. Sometimes it's just impossible. So looking at correlations is still a great thing because you're still able to measure things, whereas with naturalistic observations, you are not able to measure things. You can just describe. Now, there can be more than one variable. There can be a third variable. But again, you just want to remember that through all of this, it's correlation does not cause, or correlation is not causation. So when we have a third variable problem, then what we're seeing here is that two variables may be related to one another, but only because they're both causally related to a third. So in other words, so here we have x and y, that's a correlation, but then we add in this variable z. And variable z causes both x and y. Okay, so here this example is variable z is the lack of adult supervision, can lead to aggressiveness, and then lack of adult supervision can also cause exposure to media violence. Now, if you're only looking at the two variables x and y, we've got exposure to media violence and aggressiveness. Now, there's a positive correlation between these two variables. However, exposure to media violence does not cause aggressiveness. Similarly, aggressiveness does not cause exposure to media violence. However, this variable z causes both. Okay, so that's how the third variable problem works. And so how do you account for that third variable problem when making an experiment? What you're going to do is you're going to try to either have a matched samples or matched pairs. And this is just when you're making two groups for your experiment. You want the participants to be even. Remember that representative sampling. So you can do that with matched samples in which participants in the two groups match. So you can see here they just have these percentage things here, and you can see it's 45 or 48, 48, 48, 48. So everyone has a matched, or everything within each is matched. So the samples overall are matched. Another option is you can have matched pairs. So each participant has a match in the other group. So say this kid here, let's call him Steve, and then this kid over here, let's call him Elijah. So Steve scored 20%, Elijah scored 20%. So they're going to try to match them specifically. So this kid got 91. They're going to find another kid that scored 91 and put them in the other. So you're matching pairs in between. Now, this percentage thing's confusing, but what I want you to think about is, say, age. So let's say we have, ignore the pictures, but say in group A, we have someone that's 20, someone that's 91, and someone that's 33. What you're going to want to do then when you make your other group is you're also going to find a 20-year-old, a 91-year-old, and a 33-year-old. So you're matching within pairs. And overall what this does is it makes the mean age or the average age of each group the same. And then the matched sample is, instead of being exact with a 20-year-old and a 20-year-old, a 91-year-old, a 91-year-old, is with matched samples, all you're looking at is the average overall age is going to be the same. So say it's, again, 48, the average overall is going to be 48, but group 1, everyone could be 48 years old, but group B could be say this group, the 20, 91, and 33, which again, the average is 48. So you're averaging overall in the matched sample, and in pairs, you're matching an individual. Now, let's move on from correlation, and we're going to go to the final type of study, experimental research. So experimentation is the only way to truly infer causality in an experiment. So correlation, we only talk about a relationship, whereas with experiments, we can finally talk about causality. So A causes B. So this is really important. So again, we are looking at a relationship between the variables, but we're looking at a specific relationship of causality. So experiments allow researchers to determine the causal relationship between two variables. And we do this by using strict controls of conditions in order to determine the causality. So you have to be very strict about what you do. So there are some very important terms that we're going to have to know for experiments. The first one is a variable. I've been talking about variables a lot, but specifically a variable is a property whose value can change across individuals over time. An independent variable, or an IV, is the variable that's manipulated, okay? So we have an independent variable, and then we've got the dependent variable. So the dependent variable is the variable that's measured. So we manipulate the independent, and we measure the dependent. So pretty much what it is that by manipulating the independent variable, it'll cause the dependent variable to change. Okay, so that's how that works. So the dependent variable is dependent on the independent. So how do we manipulate variables? The point of an experiment is to manipulate the variables in a controlled environment. So what we're going to do is we're going to take a sample of the population, and we're going to split that sample into two groups, an experimental group and a control group. So in the experimental group, what we're going to do is we're going to manipulate the independent variable. In the control group, we are not manipulating the variable. So the control group has no manipulation, whereas the experimental group has manipulation. So how to manipulate? Step one is you have to determine what you want to study. So that's where that operational definition really comes into play. So you need to identify your independent variable and your dependent variable and what you're going to measure. And then you have to decide, do you want a between subject or a within subject design? So a between subject design means you have two groups of different subjects, a control group and an experimental group. Sometimes we'll call them a treatment group because they get treated with the manipulation. Now, opposite of a between subjects group, we have a within subjects group. And that's where you only have one group of participants or subjects, but they act as their own control group and their own experimental group. So really what we do here is we do kind of an A-B type situation. So first the group will go in, they'll do a task normally, then you'll introduce the manipulation, and then you'll have them do the task a second time. And so what you're doing is you're comparing their behavior from before and after that manipulation. Whereas between group subjects, it takes less time, you need more subjects, and you're just looking at the individuals that didn't do treatment and then the individuals that did. So here's an example. Let's say you want to test whether drug X increases a participant's mood. Your independent variable would be the drug, so whether a subject gets the drug X or not. Your dependent variable, so what you're measuring, is the participant's mood, okay? So how are you going to measure that now? So when I say measure here, what I'm talking about is our operational definition. So you're going to measure the mood by scores on a health and wellness survey for mood. And then we go to step 2 of manipulation. So now we need to manipulate our independent variable. So going with that same example, we're going to give the drug X to group 1. So that's going to be our experimental group. And then we're going to give a placebo to group 2. Now, a placebo is like a fake drug. So usually this will be, say, a sugar pill for a drug trial, or a placebo could be you pretend to do something. It's pretty much just a fake thing. Now, step 3, we need to now measure our dependent variable. So how we're going to do this in the example is we're going to give both the groups that mood survey. And then step 4, we're going to check for effect and draw conclusions. So we're going to score the mood surveys, and we're going to see, is there a difference in mood between participants of the experimental group and the control group. Now, when we're looking at measurements, there are a few things you need to keep in mind. You're going to need to keep in mind reliability. So your measurements need to be able to produce the same measurement when measuring the same thing. In other words, if you give someone, say, a survey for mood, and you give it to them on a normal day A, and they do a thing, and then you give it to them on normal day B, it should again be the same thing about. Or a good example here is when you're measuring weight of, say, you have a 50-pound rock. Every time you weigh the rock, it should be 50 pounds. That's reliability. And then we've got validity. So validity means that it must be conceptually related to the study. So high validity would be, say, you measure the number of smiles someone has in order to relate to happiness, right? So when someone's happy, they tend to smile more, and then again, so that's a high validity. Now, low validity would be, say, you want to measure how happy someone is, and you do that by counting the number of times they blink their eye. Now, I don't know about you, but I don't tend to blink my eyes more the happier I am. My eye blinks are not related to my mood. So that would be a low validity because it's not related to the property of my study. And then the final one is power. So power just means the ability of a measure to detect the conditions specified in the operational definition. So again, if we're talking about smiling, it's the ability of a measure to determine whether a person is smiling when they're actually smiling or not. And then, of course, the opposite, the ability to detect when a person's not smiling when they're actually not smiling. So how well is your measure doing its thing? So this is, again, where you need a good operational definition. When we come back, we're going to finish up our measurements next recording.